So good day to all. Today we can discuss about the topic of voltage regulator IC723 in the subject linear integrated circuits. So what does this voltage regulator is uh, doing is this voltage regulator, what is the requirement is mainly to the DC voltage is obtained from or the circuits should be stable. To make this stable, we are going for using this uh, voltage regulators. Generally, there are several types of voltage regulator. That is linear voltage regulator and the switching regulator. We are going to discuss today about one of the fixed voltage regulator, or it is also coming under the type of linear regulator. So, what are the thing is the normally available fixed voltage regulator is do not have short circuit and output voltage is not stable. These limitations can be overcome in IC723. So usually the fixed voltage regulator will be having the three terminal regulators such as 7805, 7815, 7905, 7915, and they are capable of producing only fixed positive or negative output voltages. The main thing is they do not have short circuit protection. So in order to overcome this, we are going to use a IC723 general purpose regulator, which overcomes the limitations of these three terminal fixed voltage regulator. So it is IC723 is a low current device, is a low current device, low current device, and it can capable of providing a load current up to 10 ampere or by more by the addition of external resistors. So minimum it is of 10 ampere. Okay. So what are the features is first one is the unregulated DC supply voltage at the input should be between 9.5 volt and 40 volt. Adjustable regulated output voltage should be between 2 to 3 volts. Maximum load current of 150 milliampere, and with the additional transistor used, it can have up to 10 ampere obtainable. So the low current device of maximum of 10 ampere. So this is the major thing it can able to provide. So positive or negative supply operation, internal power dissipation of 800 millivolt, built-in short circuit protection, very low temperature drift, high ripple rejection. These are the major features of IC723. So how it should be, how the IC structure should be. The structure, the functional block diagram is shown with the pin diagram of 14 pin dual in package and 10 pin metal can packages for the device. So both the structures are shown in this diagram. And the zener diode, the constant current source, and the reference amplifier form one section of the IC. So this V reference, everything will be coming as a separate section, and the error amplifier will be used to make the difference between that input inverting and then non-inverting input terminal. Then this current sense circuits are used. Then these are the commonly available things, parameters which is related to this IC structure. So 14 pin dual in package IC and 10 pin metal can IC. This is the current limit is the 10th pin. Okay, frequency compensation is the 9th one. So this gives you a structure of your IC723. And general simplified functional block diagram is divided into 4 blocks. One is the reference generating block, that is V reference. Then the second one should be the error amplifier. Third one should be the series pass transistor. And fourth one should be the circuitry to limit the current. So major sections it will be shown is with the, so what should be the V reference value, the reference generating block. What is the V reference value is, it is approximately equal to 7 volt. That means it is actually equal to 7.5 volts. So it should be exactly it will be equal to 7.5 volts. Yeah, it should be 7.5 volts. The series pass element is sorry. Here, the sense voltage, that is CS and CL, sense voltage, current limit and current sense. The sense voltage is the voltage drop obtained across a suitable resistor connected between the terminals. This is your output. This V naught should be your output, which is the current between the CL and CS. CS is current sense and CL is current limit. And the structure, the four structures, four functional block diagram are explained here. So the temperature compensates Zener diode, constant current source. This is your Zener diode and the constant current source. This part and this part. Okay. So with it should be connected to the voltage reference amplifier. The Zener diode is used to generate a fixed reference voltage internally. So that is the major thing of using. So you know Zener diode acts as a voltage regulator. Here it is used to generate a fixed voltage internally. The constant current source will make the Zener diode to operate at a fixed point and it is applied to the non-inverting terminal of error amplifier. So the unregulated input voltage VCC is applied to the voltage reference amplifier as well as the error amplifier. So error amplifier is a second section as per the diagram is the error amplifier, this section. So this error amplifier will be used as a high gain differential amplifier with two input, inverting and non-inverting. So the non-inverting input terminal is connected to into the internally generated reference voltage. So what is the reference voltage? It is of 7.5 volt. The inverting terminal is connected to the full regulated output voltage. Next is series pass transistor. That series pass transistor is Q1. This Q1 will be the series pass transistor. So this Q1 transistor is the internal series pass transistor which is driven by the amplifier. This transistor actually acts as a variable resistor and regulates the output voltage. The collector of transistor Q1 is connected to the unregulated power supply. The maximum collector voltage of Q1 is limited to 36 volts. So as we have studied in your features, it should be maximum of 9.5 volt and 40 volt unregulated DC supply, first feature. So here it should be mentioned as the Q1 is limited to 36 volts. The maximum current is 150 milliampere. And what is the circuitry to limit the circuit? That is the Q2. This is the Q2. So Q1 is the series of fourth one is Q2, that is the circuit to limit the current. This is the fourth section. So in this fourth section, the internal transistor Q2 is used for current sensing and limiting. Q2 is normally off transistor, turns on when the limit, that is the current limit IL exceeds a predetermined limit. So maximum it is mentioned 150 milliampere. You can have up to 10 ampere by connecting some external resistors. If it exceeds, this circuit will be going to be turned on. So it is a very, very important point here. And second, now we can discuss about the low voltage regulator using IC723 and high voltage regulator using IC723. This diagram shows the low voltage regulator using IC723. So this circuit arrangement is used for regulating voltage ranges from 2 volt. It should be from 2 volt to 7 volt. And hence it is called as a low voltage regulator. So the output voltage is directly fed back to the inverting input terminal. So the V naught is directly connected to the inverting input terminal. The non-inverting terminal, that is your fifth pin. In the diagram, you can have this fifth pin, that is the non-inverting input terminal, is obtained across the potential divider formed by these resistors R1 and R2. So hence, what should be the voltage at this non-inverting input terminal? It is nothing but V non-inverting equal to V reference, that is the voltage across this, into R2 by R1 plus R2. You know what is your V reference? It is nothing but 7.15 volts. Okay. So this error, the next is the error amplifier amplifies the difference and it drives the pause transistor Q1. It is actually, we have studied a separate. Here it is with the functional block diagram, only the limited circuit. So you can remember using that diagram. The transistor Q1 acts as control element, minimizes the difference between the non-inverting, between the fifth pin input and the fourth pin. Okay, so that is the actually input to the error amplifier. So minimizes the difference between the inverting and non-inverting input of error amplifier. Therefore, the output voltage is given as 7.15 into R2 by, it is approximately equal to the non-inverting input terminal output 7.15 into R2 by R1 plus R2. Okay. So now assuming that the output voltage is low, the inverting input terminal goes down, making the output of error amplifier more positive. This drives your NPN pass transistor further into conduction. Hence, higher current is driven into the load, thereby causing the output voltage to increase. So this is, so in a similar manner, any rise in load voltage gets regulated. So this is the given structure for the low voltage regulator. So it takes the difference between the inverting and non-inverting input terminal and the output will be approximately same as your non-inverting input terminal. And assuming that the output voltage is low, the inverting input goes down, making the output of error amplifier more positive. Next is, so this is a general purpose diagram with all the transistors. So same, this is with IC structure and here it will be shown with that's Q1, Q2 transistor, everything. Your diode, all are interconnected, error amplifier. And this is your structure of this low voltage regulator using IC723 with a detailed diagram. Next is high voltage regulator. So this IC723 can be used to design a high voltage regulator for output voltage ranging from 7 volt to, so that is low means 7, 2 to 7, here 7 volt to 37 volts. So here's the down inverting input terminal is directly connected to V reference through R3. Next, the inverting input terminal is connected. This is your inverting input terminal. This is connected to the junction of resistors R1 and R2 connected with the output V0. So the resistor R3 is selected to be, this R3 should be selected, which will be equal to R2 parallel R1. That is very important. Then the error amplifier acts as a non-inverting amplifier with the voltage gain given as AV equal to 1 plus. Here it should be non-inverting. And in the low voltage regulator, it should be in inverting input terminal. So what should be your output? Output is V0 equal to V reference. So our output is V0 equal to V reference. The V reference is 7.15. So into 1 plus R2 by R1. So how it works is, only thing is that in the circuit connections, you are going to make changes with the inverting and the non-inverting. There the dividing resistor should be across your non-inverting. Here the dividing resistor should be across in the inverting input terminal. That's the major difference. It is going to be taken place and it can generate up to 6 volt, regulate up to 6 volt to 30. So this particular IC723 is mainly for 3 purposes. One is current limit protection and the next one is foldback. Then the third one should be the boosting. First we can discuss about the current limit protection. So in this current limit protection, the limitation of the IC723 is no built-in thermal protection and short circuit protection. So therefore, the current limit protection in regulator IC is necessary for providing protection against short circuit condition across the load. So the low pass and high pass regulators discussed in the previous section has no built-in current limited circuit. So this circuit prevents the load current. What is this major thing is, this prevents the load current from increasing beyond a safe value. The operation of the circuit is the series pass element Q1, which is a part of the regulator circuit, is shown connected in series with the current limiting resistor RC. This is your RSC is the current limiting resistor. The voltage drop across this resistor can bias the transistor Q2. So this can able to, this R is because the voltage drop across this can able to make this bias the transistor Q2 and turn it on. Assume that the circuit can supply a maximum current of IL max. Okay, maximum current of IL max. So in such norm, the output voltage remains constant for any value of ICL up to maximum current ICL max, that is 10 ampere. Okay. So what when considering the load the one load current, if I naught is increasing, leads to more current through this RSC, then the voltage drop across this turns the transistor Q2 on. Hence, any current which is in excess is diverted away from the base of Q1. This effectively reduces the emitter current of Q1, and thus the load current reduces. So this is the way it will be working. Second, so it is I limit equal to V sense by RSC. It is 0.5 volt by the RSC value. So maximum value should be taken into account. So the load current produces small voltage drop across RSC. This voltage is applied directly across the base emitter junction of Q2. When this voltage is approximately 0.5 volt, the transistor Q2 begins to turn on. Now a part of the current from mirror amplifier goes to the collector of Q2, thereby decreasing the base current of Q1. This in turn reduces the emitter current of Q1. So any decrease in the load current will get nullified. Similarly, if a load current decreases, VBE of Q2 drops, repeating the cycle in such a manner that the load current is held constant to produce a voltage across this RSC sufficient to turn on Q2. This voltage is typically 0.5. The second thing is foldback current limiting circuit. So in the simple current limiting circuit, we have discussed the maximum current limit was preset such that the power dissipation will never be more than the value set by generally by V into IL, that concept. But the net effect is that the old regulator is underutilized in such condition. So underutilized. Whenever it is going to be underutilized, we are going for this foldback current limiting circuit. So in the current foldback method provides full protection to the device in addition to allowing higher currents to the load. So you can see this. This is your short circuiting that current limit. Here it will be apart from that, it is going to be even. So the thing is, how it is going to work is this foldback current limiting circuit method of over current protection is employed to reduce both the output load current and voltage. When the load resistance becomes smaller than what would shown with a specified maximum current, the current limiter protector regulator as IL max is exceeded, the output voltage of the regulator decreases. The important advantages of using this is, the major advantages, one is protecting the load from the overcurrent. Second one should be protecting the regulator itself. Protecting the regulator itself. So these are the major advantages of using this. So it depends mainly on this current limit transistor, which is connected over here. In this across this RS. Here. It's not shown fully here. This is that circuit. See this Q1, Q2, the entire structure. This is the structure of this. So this is what I have explained to you. And the last one is the high current low voltage regulator. That means boosting. So for this, the maximum current obtainable is 140 milliampere, for applications requiring high current values. Boost fast transistor Q1. So this one, this is a boost fast transistor. Boost fast transistor can be added to the regulator. So the collector of Q1 is connected to unregulated DC supply. Collector is connected to unregulated DC supply. The output terminal V0 of the regulator drives the base of Q1. This is the base. So output is connected to it. So it will be driving this transistor Q1. Therefore, what should be the I0 equal to beta of boost transistor into I0 of 723. That is a 140 milliampere. If you are using a Darlington connected transistor pair instead of this Q1 as the POS transistor, we can able to obtain higher values of load currents. So instead of this, if you are using Darlington pair of transistor instead of Q1, you can have high value of load current. These are the major uses of this voltage regulator. So we have discussed first what should be the voltage regulator with this functional block diagram, pin diagram, features. Then we have discussed about this general purpose regulator with a low and next as high. Then how it is going to use this as a current foldback current limited protection circuit and high current, that is boosting circuit. Hope you have understand this. Thank you.